A lot of the power of studying networks, and let's be honest, a lot of the fun, comes in the fact that they're easy to visualize, and that the visualizations can often show us things that we might not expect to find. Let's look at this with the data that we've been working with so far, which are these social affiliations of various people in colonial Boston. So we can look at our matrix of groups by groups like this. Each of the rows and each of the columns refers to one of the social groups, and the diagonal, the high numbers, are the group with itself. So the first group has 53 members, so the number of members that it has in common with itself is 53. Now we don't actually care about that diagonal, so we're going to get rid of it with a replace command. So our table of groups by groups now looks like this. Now that we've zeroed out the diagonal, so the first group has 2 members in common with the second group and 3 in common with the third group, and so on. Now that we have information in this form, we can visualize it as a graph. And in order to label the vertices of this graph, we're going to need a list of rules. We use the map thread command to do this. So here are our group names. The first group is St. Andrew's Lodge, the second group is Loyal 9, the third group is North Caucasus, and so on. When we have information in this form, we can use the adjacency graph command, like this, to show us information about which elements are linked to one another. And here I'm also using the image size option for this command so that it fits the full width of my notebook. Now we're comparing this figure here with the figure that Healy draws in his blog post. And what we have done is we've indicated multiple connections with multiple lines. That's the Mathematica default. What he does instead is he scales the width of a line to the number of connections that 2 groups have in common. But we can see at a glance that North Caucasus and London Enemies have a lot of groups in common. North Caucasus and the Tea Party have a lot of groups in common. London Enemies has a lot of groups in common with Boston Common, and so on. Loyal 9, out here on the edge, has very few connections with the other groups. We can also create a network of individuals in the same way, and I'm just going to scroll the blog post here for a second. Okay, so here's his network. So the network of individuals is being extracted from our person by person table. Once again, we want to clear the diagonal of the graph, and we draw an adjacency graph of the people by people with a 0 diagonal. Now notice that it doesn't actually draw the graph for us. In other words, it doesn't create a figure like Healy has over here on the right, which some people might refer to as a big hairball. It's not very useful as a graph, other than to just sort of impress you with the sheer amount of stuff in it. We can do this, if we want though, by wrapping our command in simple graph, which gives us a similar kind of hairball. Now one of the things that Healy does is he zooms in on this graph to show you the centrality of Paul Revere, and part of the fun of his blog post is showing the kind of social network position of Paul Revere. Instead of zooming in, what we're going to do is we're going to highlight the portion of the graph that refers to Paul Revere. We can extract Paul Revere's person number. He's number 200 in our list of persons. And now that we know that, we use the highlight graph command to show him in there, and we can see that sure enough, he's right in the center of all of these social networks. Paul Revere is of interest in this context precisely because he lies on the shortest path between many pairs of individuals. Healy says if we were to measure this, there's a measure of this called betweenness centrality, and Healy says it's a way of asking, quote, if I have to get from person A to person Z, how likely is it that the quickest way is through person X? Person X in this case is Paul Revere, and for many connections, for many potential connections between people, Paul Revere lies between them. We can use the betweenness centrality command to calculate betweenness centrality of each of the people in the graph. Now this is our list of 254, or however many of them there were, a list of people, and we know that Paul Revere is number 200 in this list, so we can pull his out directly. We see that it looks like a relatively high number if we scan this just kind of with our eyes, but what we can do is we can make an association to link each person to their own betweenness centrality. That's what I do in the next command, and now we can query it. We can say, what is Paul Revere's betweenness centrality? What is Dr. Allen's? Okay, Paul Revere's is very much higher than Paul Allen's. Dr. Allen's. We can also take the largest 10, and in this case, our numbers are not going to exactly match Healy's because our data set is slightly different. But Paul Revere still has the highest betweenness centrality measure, and the top 5 people here are in the same order as they are in his calculation. Now, one of the things we can do with graphs, especially when they start to become these big messy hairballs, is we can pull out a subgraph to study in detail. So for example, I'm going to pull out the top 10 names, or the people with the 10 largest betweenness centrality measures. Here they are in descending order: Paul Revere, Thomas Around, and so on. And in the next command, I'm going to pull out their position in the list of people. I can then link each person to a name like this. 200 is Paul Revere, 233 is Thomas Around, and so on. And pull the subgraph that corresponds to those people. When we look at those people with the top betweenness centrality, we see that not only are they often the people who are on a path from one person to another, but they also have a large number of connections with one another. So they're very densely connected with one another, as well as being central in the graph in this betweenness centrality sense. And we can see, if we use groups in common, we can see the number of organizations in which a particular pair of people might be encountering one another. So Henry Bass and Thomas Chase, for example, have 4 organizations in common, and presumably might have many opportunities to encounter one another. If we do this with the bottom 20 people, the graph looks like this. We have a number of isolated groups. So for example, if I just take this one in the lower right-hand corner, Dr. Allen has contacts with 3 other fellows. Each of them has contacts with the others, but they don't, for example, there's no direct contact between John Ballard and George Bray. So one of the questions we ask in these kinds of situations is, who could introduce 2 people that don't have a direct connection? One of the things we could ask is, for example, could Paul Revere introduce 2 people, say Dr. Allen and Samuel Austin? Well, he has the North Caucasus in common with Dr. Allen, and he has London enemies in common with Samuel Austin. So Paul Revere could serve as a person that could broker some kind of meeting between these 2. But he doesn't necessarily need to be the one to do this. We can get a list of all of the people who know Dr. Allen. Okay, so he's in North Caucasus. We take North Caucasus. Here's all the people in North Caucasus. Now we go to Samuel Austin. Samuel Austin is in London enemies, and here's all the people in London enemies. And now we plot, of course, the intersection, which gives us the people that are in both groups. And we can calculate the length of that. It shows us that there are 16 people, these 16 men, who could potentially introduce those 2, even though they have no direct connection between them.